All right. Well, last time we talked about composition, so let's continue talking about composition. Talk about domains of compositions here, and we'll also talk about how we can split a composition into different pieces. And then we'll get into some new stuff as well today. So let's look at this next example. We've got f of x is 3x squared minus 5. G of x is 3x minus 1. And this is asking us to find f composed with g. So how do we accomplish that? What is that equal to? How do we compute it?
G of f. Oh, f of g of x.
Yeah, it's f of g of x, right? And then we put the g of x in, the 3x minus 1, right? The g of x is 3x minus 1, so we replace that. Now where does that 3x minus 1 go?
Inside of the 3x squared.
Good, yep. So it goes 3 times 3x minus 1. Ooh, hey, it's a little small. Squared, is that a minus? Good. 5. And that is the composition, right? We took out the x, we put in the 3x minus 1. We could multiply it out. What do you get when you multiply out 3x minus 1 squared? So I got to multiply it by itself, right? 3x minus 1 times 3x minus 1. There you go. Yep, 9x squared minus 6x plus 1. We got to do the distributions, right? Then we can distribute the 3. And finally, we can combine those constants on the end. And so you should get 27x squared minus 18x minus 5. Look familiar from last time? Okay. What if you wanted to do g composed with f of x? What would you do this time? Oh, it's not minus 5. It should be minus 2. Yeah. I just rewrote the minus 5 again and didn't simplify it for some reason. So g composed with f of x is what? And g of f of x. So what do we do next? Okay, yeah, we put the f into the g, right? So f of x in this case is 3x squared minus 5, right? So what do you get when you plug that into g? Then minus 1 on the end, right? Take out the x, put in the 3x squared minus 5. Distributor of 3. Let's see if I can simplify my constants correctly this time. You get 9x squared minus 16. Not okay? No? No, not okay?
It can be simplified to...
Oh, you can factor it, you mean?
Yeah.
Yeah, you can factor it, but as far as being simplified, that's about as far as it can go, except for breaking it apart. If you were trying to solve an equation, then yeah, you might want to be able to factor it. But is this okay with the process? So what's f composed with f going to look like? Yeah, plug f into itself again. So that's f of x. F of x again is 3x squared minus 5. So what is that going to look like when you plug that into f?
3 of 3x.
Minus 5. Squared.
Good.
Minus 5.
Yep, good. And I'm not going to take the time to multiply that out, but this is what you get, right? We're going to go back to the original f, the 3x squared minus 5, and plug in 3x squared minus 5 where the x is. So I can do f of x. I can do g of x if I wanted to do it. They don't have to be separate functions. I can do the same function over and over again. If you bake anything, maybe bake some bread, you might knead the dough and then roll it back out and then knead it again and roll it back out and knead it again. It's just the same function over and over again, right? Same kind of concept. All right. This okay with doing the compositions? Okay. The one tricky part with compositions might be the domain. Okay? You have to be careful with domain. So let's look at this example and see why we have to be careful with domain. Pardon me. So this one's asking us to do g of f of x and then, g composed with f of x, figure out the domain, and do f composed with g and do the domain. So let's do the first one. Again, this is g of f of x. F of x in this case is root x minus 4. We plug in root x minus 4. What do we get? Okay. So again, take out the x, put in root x minus 4. So we get root x minus 4 quantity squared plus 4. What happens with your square root and your square? Yeah, they go away. Yeah, they cancel each other out. You get x minus 4 plus 4, which we just end up at x. We'll worry about domain in a minute. What do you get when you do f of g of x the other way around? Yeah, so you've got root x minus 4 in there. Good. Oops, the other way around, right? I got this back. No, I don't. My g of x is different. I got this backwards. Sorry. This is x squared plus 4. My bad. Yeah, g of x is x squared plus 4. Where does that go? Yeah, it goes inside the x minus 4, right? So we'll get x squared minus 4 plus 4. Underneath the radical now we have x squared. And what happens now with your square root and your square? Yeah, they almost cancel out. We actually have to be a little bit careful when we do these. This is actually technically absolute value of x, not just an x. And here's why. If I do square root of 2 squared, that's square root of 4, which is 2, right? So I really do get back to where I started. But if I do square root of negative 2 squared, what happens when you square the negative 2? What do we get under the radical? It's still positive, right? When I take negative 2 and square it, I get 4. And now square root of 4 now is 2. Do I get the same thing I started with? 2 is the same thing as negative 2? Those are different, right? This was x here. That's not x anymore, is it? Yeah. The answers are the same, but we don't get the same thing we started with, right? Here we started with 2, we ended with 2. But here we started with negative 2, we also ended with 2, right? So technically, when you do square root of x squared, you get absolute value of x. It kills the negative off. Okay. All right. In any event, that's how we get those different compositions. But now the problem also asks us about domain. If all you did was look at your final answer, what would you say the domain is for both of them? It was like all real numbers. You'd be wrong. Only one of them is all real numbers, not both of them. Okay? Here's why. Remember when we do composition, where's the first place the x has to go into? Look, when we do a composition, does it go inside the G for this one? Does it go inside the G or the F first? The F, right? It goes inside the one that's on the inside, right? Okay. What is f of x in this case? It's root x minus 4. What can you not plug in to f? A negative, right? I can't have a negative under the root, right? Okay. So since, in this one, since the domain of f of x is 4 to infinity, my g of x can't, or my g of f of x can't have a bigger domain. Okay, so the domain doesn't change in this case. G of x has no problems. That's one of the reasons why it doesn't change. All right, so the domain of f of x is 4 to infinity. I have no problems with my g of x function, but I don't magically get no problems overall, even though the square root and the square cancel. Do I have the same problem here? Well, notice under the radical, do I get any negatives under the radical here? No, because I'm squaring the x value, whatever we plug in, right? I don't get any negatives. So in this case, the domain's going to be all real numbers. The moral of the story here is if you're checking domain of a composition, check it before you simplify. Okay? Write this down. I'll even write it in red. Check the domain of a composition before simplifying. Okay. Don't do it after. If you do it after, you might get, well, something wrong. Okay? All right. Work on the next one for a minute, and then we'll chat about it. Rewrite f composed of g of x. We write it as
1 over x minus 1.
Okay, I agree. So, yeah, we'll go step by step here. The first step would be to write it as f of g of x, right? Okay. And our g of x here is x minus 1. And when we plug that into f, we get 1 over x minus 1. And there's not a lot of simplifying to do on this one, right? It's about as good as it gets. So now if you look at this function here, what can go wrong? You divide by 0, right? We've got a fraction. When would you divide by 0? What number would you plug in for x to get 0 out? 1, right? So what's the domain? Okay.
And then 1 to positive infinity.
Good. Yeah, we need to delete out 1, right? 1's the number we can't plug in, right? We need to make sure that if we do set the denominator equal to 0 off to the side here, we get x equal to 1, and that's the thing we don't want, right? So we delete it out. Okay. What about the other way? If we do g of f of x in this case is 1 over x, and we get and 1 over x, and then minus 1, right? On the outside of the fraction, correct? Because we're just taking out the x and putting in 1 over x. Okay? Yeah? Okay. Now, again, we could get a common denominator to combine this into a single fraction, but if we're looking for domain, I really don't want to simplify. I just want to look at this piece. What do you not want to plug in for x? 0, because the x is just in the denominator now, right? So we delete out 0, so your domain will be what in this case? Yep. Good. That okay? You make it okay? So again, we're doing the same thing, right? Making sure that our denominator is not equal to 0 here. And in this case, there's just a single x in the denominator, so it must just be x can't be 0. All right. One of the things that's helpful later is being able to break a function into pieces. In particular, being able to write a function as kind of an inside piece and an outside piece. There are a lot of these problems. There are multiple ways to do that. But looking at this particular function, in particular, let's look at that piece right there. You kind of see an inside piece and an outside piece, right? There's an inside piece of doing the negative x cubed plus 3. And then there's an outside piece of a square root, right? So when we're asking us to write this and breaking it into pieces, notice it says we want f of x equal to g of h of x, essentially, right? So the h, if I think about what this looks like, this is g of h of x, right? What do you think, if this is supposed to be the inside piece here, what do you think you would let your h of x equal? I just said, look at this piece right here. You identify an inside and outside. You told me an inside. What do you think you'll let h of x equal? Yeah, the negative x cubed plus 3. That inside, what's under the root, right? That's the inside. Then what do you think the g of x would be?
Root x minus 5.
Yeah. Right? Because notice if we do the composition, if you do g of h of x, where does this x cubed plus 3 go into? Goes into the x, right? We end up exactly where we started. Now again, this is not the only way to do this. Do you see another way you could do it? This is not a unique way to do it. Do you see another thing I could have used for an inside function? There are lots of different possibilities. You see there's something else we could have used for an inside function?
Negative x to the third.
Yeah, you could do that. So you could do x cubed as the inside, and then you could do your g of x as negative x plus 3 minus 5. You could do that. Absolutely. Because again, the x cubed would go in for the x, right? See another way? See another inside and an outside?
X squared and then the root negative x. No, I messed that up midway.
It's like, I don't think x squared would be harder. I could do it with an x squared, but it'd be uglier.
The whole square root portion as the h, and then minus 5 or x minus 5 for the g.
Yeah, you could absolutely do that. I could use that whole square root of x, negative x squared plus 3 as my h, the inside. Because I could think again, I would take this whole thing and plug it in for the x. That's exactly right. It's another way. That should be an x cubed, not a squared. Sorry. There's lots and lots of different ways to do it. There's no one right way to do it. Okay? I could have done, I could have made this just a positive x and made that a negative x cubed, for example. Okay? Lots of different ways. All right. Let's see if we can do the next one here. Now this one might be a little bit more obvious of what to let the inside and what to let the outside be. Still do it multiple ways, but this one might be a little bit more obvious as to what to let maybe even the outside function be. what does it look like your outside function is? What would be the thing you would do last if you were to plug in a number for x? You could use it. Yeah, you could absolutely use 3 minus x. I'm just thinking of it like if you just took a number and plugged it in for x here and went through the whole process of simplifying it, what would be the absolute last thing you would do? Yeah, you do the absolute value, right? That's why I use the word absolute. It's the absolute last thing you would do, right? Because if I notice what it says to do. Plug in a number for x. What do you do first? Take the reciprocal, subtract it from 3, and then take the absolute value. The absolute value is the last thing you do, right? So if I use that for my outside function is represented by the g here. What's on the inside of the absolute value? 3 minus 1 over x. Yeah. Sometimes it's a little bit easier. Sometimes I think it's easier to identify what's on the outside and make that your kind of overall function, right? So if you had, let me just do another example off to the side before we do that last one. What if you had your f of x was, say, 2x plus 5 to the 4th power? Again, think of g as your outside, h is your inside. Again, if you're putting something in for x, what would be the last thing you would do to simplify? If you were putting something in for x, what would be the last thing you would do? You take it to the 4th power. So what should your outside function be then? X to the 4th. Good. What's on the inside of the 4th power in this case? 2x plus 5. So I'll make it 2x plus 5. Is that making sense? Yeah? Okay. All right, let's look at this last one. This one's wanting us to do it in pieces. Okay? Instead of breaking it up into 2 pieces, it wants us to break it up into 3 pieces. A little bit more complicated. All right, so notice we've got 2 over square root of x plus 4. Okay? Now, we said it that way on purpose. 2 over square root of x plus 4. Again, if you're doing something, plugging in for x, I would either work out inside out or outside in. Whichever way makes more sense in your brain, do it that way. Okay? If I do it inside out, what looks like it's the thing that's on the most on the inside? X plus 4, right? So what we would let our j of x here then be the x plus 4. That's the thing that's on the inside. What's x plus 4 inside of? The square root. So what do you think you'd let the h piece equal? Square root of x, right? Yeah, good. And then where is the square root? It's in the denominator, right? So what should you let your outside thing be? 2 over x, yeah. So that was thinking about it inside out. You could also do it outside in, right? That was the way I said it, correct? The thing you notice is it's 2 over something, right? So my outside function is 2 over x. What is it over? Square root of something, right? So my next one, square root of x. Finally, what is the square root of? X plus 4. That makes sense? You want to see one more like this? I can make another one up. Yeah? Okay. Let's say you did... pardon me. Let's say we had f of x is absolute value of, let's say, x plus 2 squared minus 5. Either work inside out or outside in, doesn't matter. And again, we'll break it into 3 pieces. We'll use G for the outside most and J for the inside most. You want to work outside, inside out or outside in? Inside out? Okay, so start with the J. What did you use for your inside?
X+2.
X plus 2. That looked like it was on the way on the inside, right? Good. I like that. Then what did you use for the H?
X squared minus 5.
X squared minus 5, because the X plus 2 is inside the square, right? And then finally, the outside is absolute value of X. Yeah. Good. Yeah. So inside out, I see this is inside of squaring, so I made that my inside function. Then I treat that like it's an X, made X squared minus 5 for the next one, and that's all inside the absolute value. Working the other way around, absolute value of, right? So I have the absolute value as my outside. Something squared minus 5, that's the next one on the inside, and then finally what's on the inside is the X plus 2. That okay? All right. Let's look at some new stuff. We just keep on trucking, don't we? What we do. So this next section talks about what we refer to as one-to-one functions and inverse functions. So, what do we mean by something being one-to-one? Well, let's look at a specific example, and then I'll come back to the definition. If you had just your function is f of x equals x squared, can you think of 2 different things to plug into that function and you get the same thing out? Well, give me an example. 2 and negative 2? Sure. F of 2 is 4. F of negative 2 is also 4, right? So notice I've got different things that we plugged in, but got the same thing out. Right? And if you think about what one-to-one should mean in your brain is that if I put 2 things in, you think I should get the same thing out? No. If I put different things in, I should get different things out, right? So that's exactly what it means to be one-to-one. So writing it in words, we would say distinct inputs give distinct outputs. Writing it in symbols, we would write if x1 is not equal to x2, then f of x1 is not equal to f of x2. Not equal to is the same thing as distinct, right? Okay. Again, just kind of in your brain of what you think of what one-to-one would mean. If I put different things in, I should get different things out, right? That kind of makes sense, right? I match this one thing with this one thing. I don't want to match something else with the same thing. That's not one-to-one, right? Then you have to share, okay? All right? So one-to-one, different things go in means different things come out. That's the symbol version of it. All right, so let's look at this example. Remember one of the first things that we did with, yes, do you have a question? No? Oh, okay, sorry. Look at one of the first things that we did with functions was write them as sets of ordered pairs. Do you see two inputs that are associated with the same output? Yeah, 1 and 4 do, right? So if I think of this as a function, if I think about it just as writing as an f, this would say f of 1 equals 3, and the second one would be f of 4 equals 3, right? We have two different things that give us the same output, so it's not 1 to 1. Now, even though one of our first things that we did with functions was write them as lists of ordered pairs like this, usually we're doing function notation, right? And making lots of things that we plug in, not just a few things to plug in. So we probably need a better method for determining 1 to 1. So let's look at this next example. We've got f of x is x squared minus x minus 2. So we'll learn a little bit later that this is how to get the general graph for these. But it should look like an x squared graph, which we already know looks like a U shape. Call those parabolas, right, for x squareds. Okay. You could also set it equal to 0 and factor it and see that it'll cross the x-axis at -1 and at 2. Okay. Now, the idea here is, though, is this 1 to 1? Now, looking at the graph, can you see where you've plugged two different numbers in and got the same number out? Yeah, -1 and 2 are examples, right? Cross the x-axis here, cross the x-axis here, right? We see that f of -1 is 0 and f of 2 is 0. So it's not 1 to 1. Now, do you see any other places? Oops. See lots of other places, right? I hope. In fact, if I take any horizontal line that actually intersects the graph, -1 point, but if I take any horizontal line that intersects that graph, how many places of intersection do you see? How many places across the graph? Got a couple of places, don't we? 2 places? All right? So every time we cross that horizontal line, that's going to have the same output, right? Whatever we plugged in here to get to that height is the same thing as whatever we plugged in here to get to that height. So that horizontal line crossed more than once. What about the next example? If I do that same trick with the horizontal lines, how many times do you intersect? Just once, right? We only get one intersection, don't we? Okay. So this one is 1 to 1. All right. So this is exactly what we refer to as is the horizontal line test. So a function is 1 to 1 if and only if every horizontal line intersects the graph of the function. Oops. At most one time. That should remind you of another line test that you have. What's the other line test that we have? Vertical line test, right? A vertical line test is used to determine if a graph represents a function. Okay? Horizontal line test is that function 1 to 1, right? So it can be a function and not 1 to 1. Just look at that x squared minus x minus 2 example, right? That passes the vertical line test, but does not pass the horizontal line test. Okay. All right. Why do we care about 1 to 1 functions? Well, 1 to 1 functions allow us to undo things and come up with what we refer to as inverse functions. All right. So, for example, what I mean by undoing if I go back up to the very, very first thing that I said, in looking at this f of x equals x squared, if I told you that 4 came out of that function, can you tell me with 100% certainty what went into the function? No, because two different things did, right? So I can't undo squaring and get a unique answer, right? Because I just don't know what went in first. It could have been 2, it could have been -2. I don't know which it was, right? Okay. So if I want to undo a function, I want to make sure that there's one and only one possibility. That's why we want one-to-one functions, okay? So if we have a one-to-one function, then we can define the inverse function. This is going to be, the inverse function is defined as y equals f inverse of x if and only if f of y equals x. Not a very it's not the most satisfying definition in the world. Okay. But notice what it's trying to do. This input here into my inverse function is the output for the original function, and vice versa. The output for the inverse is the input for the original. Okay? So it's flipping around the roles of x and y. Inputs become outputs, outputs become inputs. So rather than given an input and find an output, it's basically asking you to solve something. Here's what the output was. What must have gone in? It's the reverse. Okay. Now, one thing that I want you to notice, this is very, very important, is this notation right here. This looks like an exponent. It is not an exponent. Okay. This is the notation for the inverse function. I know that you're used to seeing a negative exponent means flip it upside down, right? That's what negative exponents typically tell you to do, okay? That's not what this means for functions. This means take the inverse function. If you want to take a function and flip it upside down, you'd have to put a whole exponent on the outside of it like that. This means flip the function over, okay? Right, so be careful with the notation. This is not a negative exponent. Okay? Very important. That does not mean flip the function upside down. Okay? It means find the inverse function. All right. How do we find inverse functions? That's kind of the point of this whole section, is how do we find them? All right. So the first thing we're going to do is that we're going to pardon me. We're going to interchange all x's and y's. Now, the good news is there's only going to be one y ever. Every x becomes a y, and y becomes an x. Okay. And then we're going to solve for y. That's the next step. And then we just write that y equals f inverse of x. So we're done. Okay. All right, so how do we do this? All right, so it says find the inverse of f of x equals 5x minus 2. All right, so remember, f of x is the same thing as y, right? We put in an x and we get out a y. Right? So the first step is to flip-flop your x's and y's. So if we flip-flop the x and y, we get x equals 5y minus 2. The next thing says to solve for y. What do you need to do to solve for y now? Add 2, good. And then after we add 2, we divide by 5, good. Erase that 5 to make it not look so funky. Now we've got y equals something with x's. So that tells us that our f inverse of x is x plus 2 over 5. Those are the steps. Okay. Let's do another one. A little bit more challenging. Okay. So this one says y has to equal 1 minus 2 square root of 2x plus 5. First step is to do what? We got to do something first. You got to flip the x and y first, right? Yep. Yeah, got to flip-flop them. And then we'll subtract. Okay. So we'll subtract the 1 over. Next step. Yeah, so we still need to solve for the y, right? So what's the next step in solving for the y? You got two options.
Divide.
Yeah, divide by the negative 2. Get the root by itself, right? Okay. But divide by negative 2. I get that. Then what? Square both sides. Good. And then?
Minus 5.
Yeah, subtract your 5. And then finally, divide everything by 2. So divide both sides by 2. And then we'll replace our y with f inverse of x. And get to the final part there. Now, you could multiply out what's in here. In particular, notice if you square the negative 2, it becomes positive, right? So I could just get rid of the negative if I really wanted to. This is the process, and this is the inverse. However, there's something a little bit strange that's going on with this particular one. If you were to multiply this out, do you see that you would get an x squared? Yeah? Right? What do x squared graphs look like? Like this, right? Is that 1 to 1? No. Okay. How did that become the inverse of that thing? Something weird's going on, right? Okay. Let's think about it for just a second, and then we're going to come back to this idea next time. What undoes squaring? What function undoes squaring? Square root, right? We define a square root function as undoing squaring, right? Agreed? Okay. Well, but x squared, you just told me, looks like this. Does that have, is that 1 to 1? No, we said a function has to be 1 to 1 in order to have an inverse, didn't we? Okay. How do we end up defining the inverse of the squaring function? Well, we do something that's referred to as restricting the domain. Okay? We cut off this part and only look at the part over here. If I only look at the right-hand side of this parabola, is that 1 to 1? Yeah, it passes the horizontal line test, right? So to define the square root function, we first restrict the domain of y equals x squared to the interval from 0 to infinity. That's how we define the square root function. It's also why we refer to it as the principal square root, right? When you say square root of 4, you say 2, right? You don't say negative 2. You say square root of 9, you say 3, not negative 3, right? That's what we mean by principal square root. We use the positive and not the negative. It's because we're talking about inversing the right-hand side of the squaring function. Okay? So back in that example that we did, which is a little bit more complicated than what I really want to talk about, what you've done is, for that particular example, you'd have a parabola that looks like this, and you've restricted it to one side or the other. In particular, in that example, you would ignore this side, and it was restricted to the left-hand side. Okay. All right. But anyway, anytime that you're trying to do an inverse of a squaring, for example, you have to restrict the domain first. That's the idea. All right. We'll talk more about inverses next time. Have a good weekend, and we'll see you on Monday.